Hello students, welcome to my channel. So today we are going to start a topic whose name is field. So let me write down the definition of the field first. So you can see I have written the definition of the field. A field is a real or a complex valued function which assigns unique value to every point in the space. So we can always represent a field with some mathematical function, and with that function, whenever we put different values of the space points, you will always get a unique value as a result, as an output. So this is the definition of the field. So actually the field are of two types. Some fields are vector in nature, some fields are a scalar in nature. Let me write their definitions now. So you can see I have written the definition of the scalar field. A scalar field is a function which assigns a unique scalar value to every point in the space. So there are certain examples of the scalar field. So for example, distribution of temperature in the space, it is a scalar field. Similarly, pressure distribution in the space is also a scalar field. Electric potential you have studied in your school classes. This is also an example of scalar field. And gravitational potential is also an example of a scalar field. Let me now write down the definition of a vector field. So you can see here that I have written the definition of vector field. A vector field is a function which assigns unique value and direction to every point in the space. So examples of vector fields are, you already know, electric field, gravitational field, and magnetic field. These are the examples of vector fields. Let me write now some properties of fields. So properties of fields. So let me write down the first property of the field. So this is the first property of every field. Every field is continuous in nature. The meaning of this is, suppose this is a source of field and it is applying field. So suppose there is some point A. Here we can have the field. Field is present. And there is some point B. Field is also present at B. So the effect of source can be felt at A and the effect of source can be felt at B. So if you join A with B, then all points between A and B should have the effect of the source. So there must be effect of source at all points between A and B. So this is the definition of continuity. So you should have, if there is a field at 2 points, then there must be field at all points joining these 2 points. So the field is always continuous. Let me write now the second property. So the second property, you can see here I have written field is always single valued. So it means if there is one point in the space, let us say this point P is there in the space. So at this point P, you cannot have two values of the field. So you will have only one value of field at a point. Only one value of field at a point. Is allowed. Let me write now the, however, please remember, but two different points in space can have can have same value of field. This is allowed. Please remember, you cannot have two values of field at one point, but you can have same value of field at 2 points. So this is allowed, and please remember this. This is something very important for us. So this is allowed. Let me write now third property of the fields. So this is the third property, and it is particularly related to the scalar fields. All scalar fields possess isosurfaces. So what is isosurface? An isosurface is a surface obtained by joining all points in space having same value of scalar field. So we already know about isosurface. So example of isosurface is equipotential surface that we have studied in lower class. Let me write now the fourth property. So this is the fourth property. All vector fields possess field lines. So for example, electric field is a vector field, and in case of electric field, we have electric field lines. Similarly, in case of magnetic field, we have magnetic field lines. So, but is important to remember this. You can remember that the scalar and vector fields are normally related to each other. Are normally related to each other. And please remember, a scalar field usually represents potential energy surface of a corresponding vector field. For example, if F vector is a force applied due to a vector field, due to vector field at a point, and U is potential energy given by scalar field at same point, then force is equal to negative of the gradient of the potential energy. So I will tell you about this gradient in my next part of the topic, where del vector is an operator which is given by I cap curly upon curly x plus j cap curly upon curly y plus k cap curly upon curly z. So this is the important point that we must remember, that every scalar field is related to corresponding vector field, and the relation is that force applied by vector field is always equal to negative of the gradient of the potential energy of scalar given by scalar field. Here U is the potential energy and F vector is the force applied.